Hello and a warm welcome to all of you who will be watching in some time the celebration of the periodic table day in English for high school students. The periodic table day celebration might be sounding to all of you a little weird, particularly in many countries, including India. Every year we do not celebrate the periodic table day. I was really influenced by the American concept when I visited 2 years back, maybe 1 year before last year, in 2024. Yeah. I was staying with my children at US in San Diego, California, where my little granddaughter, Myra, who was studying by that time, class 7, told me that, Grandpa, we have a periodic table song. Do you want to hear? I said, yes, why not? Because uh, she knew that her grandpa, means me, is a lover of music, in any form of music. So I immediately wanted to hear that, and she gave me, she gave me the link, and she brought her mobile and played that video, SAP Science US. That is a very, very popular periodic table song of about 3 minutes duration. Excellent. I was really impressed. And I thought, being an Indian, I thought possibly the accents, the US accents, and the pace with which they are, the singer and the chorus is moving ahead in that song might not be compatible, matching with Indian requirements, or countries where English is not the native language. We speak English, but English is not our native language. We are not native English speakers. Therefore, I had a determination when I return back to my home country, I would definitely make a periodic table song compatible for non-native English speaking countries, particularly non-US, because they can understand the American accents are little different, even from British accents. You can tell me which accents I am following or I am having. Maybe you will find a hybrid of everything. British, little more, Indian, of course, I'm an Indian. And of course, US, I used to stay in US almost in every year. I stay about 4 months. So must be some influence. So what is the need of observing periodic table day? Because the periodic table containing 118 elements is the spinal cord of not only chemical sciences, but all forms of science and technology. The elements, the different elements have versatile applications in the field of electronics, in the field of, mm, green energy, everywhere, technology, engineering. So therefore, periodic table day, I wanted to learn from the internet search why Americans they celebrate on every February 7th. Every year for the last maybe 15 years, February 7th means in high schools there will be a lot of fun fair. Of course, it is not an official holiday for school, but it is a conventional, not a holiday, but a celebration day in high school. The students are given different projects. They present some talks. They make a lot of fun. The mood point is to get the students acquainted or get a better feel and attraction towards the great periodic table and periodic classification. In fact, when I nurtured the idea of having a periodic table day in India, for not only Indian students alone, but all over the world, if I make it an English program, that students from all over the world will benefit, not necessarily Indian students. Because I will be, exuding a 40 plus years of my experience in teaching chemical science, chemistry. Oh, by the way, I am Sudhanshu Tripathi, a retired professor of chemistry from a local university, Ravenshaw University. But I have been engaged for the last 23 years after my voluntary retirement to popularize chemistry, chemical science in school level. We have an NGO called the Uranium, pronounce uranium, the uranium, which works for the advancement and popularization of chemistry, chemical sciences, and allied sciences in the high school level. And from the last year, we have started observing both on 7th. I'll tell you why 7th February. Because on this day, 7th February 1863, 1863. Now it is 2026. 1863. John Newlands, a British chemist, he for the first time suggested that there is a musical analogy to the recurrence of similar elements after some fixed interval. He was really enthused by the Pythagoras musical analogy that every star, every planet, every celestial object has its own vibration, has its own sound, which is musical, melodious. So that concept he took, and in fact, he found for some few elements, maybe 20 elements, he found a certain trend that after every 7 elements, the 8th element is a repetition of the first. A repetition means the new element, of course, but its properties are very, very close. For example, lithium, after lithium, taking lithium as 1, count 1, 2, 3, 4, 5, 6, 7, 8th element will be sodium. And again, sodium 1, 2, 3, 4, 5, 6, 7, 8. The 8th element with respect to sodium taken as 1 was potassium. All these are alkali metals, very, very soft and very, very reactive, having valency 1. So this trend he found for the first time. Of course, now you will find that after 8 elements, the 9th element is the repetition, not after 7 elements. Because at that time, noble gases were not discovered during the time of Newlands, but he was the first to arrange the elements. At that time, about 62 or 63 elements were discovered, and he could arrange them in the order of increasing atomic mass. At that time, they were calling atomic weight. The atomic weights were determined, yes, in a very, very crude way. And he could find such a musical analogy, just like in any form of music, made be Western music, uh, in C scale, C, D, E, F, G, A, B. Then again, C is repeating the higher octave, C. In Indian music, it is sa re ga ma pa dha ni. Then sa is repeating. So after 7 notes, the eighth note is a repetition of the first note. Similarly, the second note, that is D in Western or Re in Indian, is repeating after 7 notes. Re ga ma pa dha ni sa re. In some European systems, they call do re mi fa sol la ti do. So in fact, that really thrilled me. In fact, there was a debate. There was a long debate among the high school teachers, chemistry teachers, whether to honor Newlands for his famous law of octaves. That what I was saying, law of octaves, and make February 7th as the day for celebration of periodic table day, or the following day, 8th, that is today, 8th February, that is the birthday of the father of periodic table. Can you tell me who is the father of periodic table? It is Mendeleev. Mendeleev. So they debated for a long time. Ultimately, the consensus majority opinion went in favor of the Newland, who for the first time said there is a regular trend in the repetition, which at that time he told about Sare Gama Padani or Do Re Mi Fa Sol La Ti or C D E F G A B. At that time there was no noble gases, but the very, very fact that the repetition occurs after a fixed interval, that is new. So they started observing the periodic table day in all high schools on February 7th. In fact, we did observe yesterday into other vernacular medium schools. We had an online program. We used to visit to different schools on invitation and have a better impact. We interact with the students, we disseminate our experience, mobilize them, motivate them, demand questions from them. And while we interact, that is the real charm of the entire program, when we interact with the students. So, good afternoon, those who have started watching from the YouTube. Now, a live program going on. We shall be doing a lot of fun. And I tell you, today is the birthday anniversary of the great man Mendeleev, Dimitri Mendeleev, on which day we are now celebrating the periodic table day. Yesterday, we did celebrate following the American school of thought. We did honor them. And we urge upon all the schools of not only India or elsewhere, throughout the world, to definitely dedicate a full day in your school, may it be on 7th of February, 8th of February, or even March 6th. That is the day when Mendeleev proposed his first periodic table. Whichever day you like, but you keep your students, 9th, 10th, 11th, 12th, standard students, whoever is available, to do something on periodic classification, periodic table. Yeah, I was telling that I took it as a challenge when I heard about an American ASAP song on periodic table song, where a student can easily remember all the 118 elements easily by singing that song maybe again and again. So I thought, we'll be doing separately in a different way. Our melody, of course, the melody will make use of these 7 notes. 7 notes, of course, there are some soft and hard notes, 5 more notes. So there are altogether 12 notes in music everywhere in the world. 7 normal and 5, 4 soft, and little hard is the Tibra Madhyam, as we call in Indian. So altogether 12 notes. All the music that we hear, may it be good to hear or bad to hear, is composed of in a combination of 12 notes. A melody is one which makes use of the notes in such a manner, it gives a soothing effect, a very calming effect, a very scintillating effect on the mind. If the notes are weird, even if we are speaking using the same 12 notes, but it will be not giving us that comfort or calm. So first let me start with our periodic table song. And that song, I'm I'm happy, no doubt. I'm happy to tell you that that was not composed by me. I have already told I'm Sudhanshu Tripathi, retired professor of chemistry, now engaged in popularizing my religion. Some call I'm a Hindu, some call I'm a Christian, I'm a Islam, I'm Mohammedan, and I say I profess my religion, chemistry, chemical science. That's my religion. So I popularize that, and today I'm sharing now my screen with you. Now see, what you do, you just start your YouTube page in your mobile or anywhere in your desktop or laptop. And then in the search panel, you just write periodic table song. And when you enter it, you will not find our one at the top, because yesterday we played it. It is coming at the top, but no doubt this is the most popular American periodic table song that my 12 years old, now she is 13, 12 years old, no, is 14, 13, at that time 12 years old granddaughter played in my presence. I was really motivated. You can hear 59 million views 8 years ago. And this is our logo, uranium. This is our logo. This at the right hand top corner. So you will find that our caption is, can you sing the periodic table? Yes, easily after watching this video, the periodic table song, the uranium, you will find. Maybe after 2 to 3 or 3 or 4, sometime second, sometime third, you will find. Because it has already had 4.6K views in 1 year, but it needs more. Since we are not making any publicity, I'm a retired person. I do not have much, supporting mechanism to spread it on a national or international basis. I make some programs like this so that people will find access to our song. This has been composed. Composed means all the elements are known, but the melody that I have put, and it has been recorded in a professional studio. Now let's listen. 18 elements belonging to. Are you able to hear? Please write in your chat box that you are able to hear. Message me in the chat box. You are able to hear.
The uranium presents the periodic table song. To easily remember, 118 elements belonging to 7 periods, 18 groups, and 4 blocks. The S block in the left, the P block in the right, the D block in the middle, the transition elements, and the F block below the table, the lanthanides and actinides. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, number 10. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, 18. Potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, arsenic, selenium, bromine, krypton, 36. Rubidium, strontium, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium, indium, tin, antimony, tellurium, iodine, xenon, 54. Cesium, barium, lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, orbium, thulium, ytterbium, lutetium. Lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, mercury, thallium, lead, bismuth, polonium, astatine, radon, 86. Francium, radium, actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendeleevium, nobelium, lawrencium. Selenium, Rutherfordium, Dubnium, Seaborgium, Borium, Hassium, Meitnerium, Darmstadtium, Roentgenium, Copernicium, Nihonium, Clarobium, Muscovium, Livermorium, Tennessine, Organation 118. End of periodic table for now.
So, hello and welcome. Today, we are going to celebrate Periodic Table Day in Odia. Parjayo Sarani Divas. So, let's start. Are you able to hear me? Those who are watching from the YouTube can chat with me. Let us. This is the long form of the periodic table that first, the periodic table that you find in your schools, in everywhere in the chemistry department or elsewhere, in a teacher's room, in laboratory, in classrooms, everywhere is this new modern periodic table called the long form. And all the periodic table song has been based on this long form. So let's talk a little about this long form. Don't write anything, just listen. We'll be doing a lot of fun, and I'll be asking a few questions to you. And if you want, you can ask questions in the chat box. You can just put your questions to me. And you see, the first period, the song has hydrogen, helium. So this has 18 groups. And the left portion has two groups, 1, 2. In the erstwhile naming 1A, 2A in Roman, 1A, 2A. This is the left portion or the S block, where the electrons in the valence cell, the last cell, enters in S orbital. That is why it is called the S block. This is S1, 2S1, 3S1, 4S1, 5S1, 6S1, 7S1. This is S2. So the entire block is called S block, the left portion. If you are a class 9 student, you do not know about electronic configuration, then I will say left portion. But yeah, you can understand the electrons, they are distributed in different cells, and the last cell, the different orbitals, and the last electron is in the S orbital. That is why the S block, S1, S2. And then the right portion, these are the 6 groups. The vertical columns having elements with similar properties, they belong to a family, they constitute a family, those are called groups. And the horizontal rows are called periods, that you know. And let me tell you, Pimsen sir, principal sir, good afternoon. So you're starting for the English medium school guys, and in fact, later students from not only India but also all over the world who can understand English can watch, undoubtedly, because some of my viewers, as I have seen in my analytics, comes from US, because I stay sometime, maybe 4 months to 5 months every alternate year or every year, sometimes every year, sometimes alternate year. So I have some contacts. So I think this is going to be a very, very interesting session. We'll be doing a lot of fun. And I assure you, and I promise, when I talk about elements in the periodic table, although to many, in fact, long, long ago, I was taking this subject as very, very monotonous, boring. Let me concede what I had in my mind maybe a decade or 2 decades before, that such a topic can be presented in a forum for a long time. We had a 1 day session in Puri, in a school, 1 day session. Of course, that was in a vernacular medium, and that, the district education officer took all measures to filter the A1 students, the good students who have the strong knack in science, to isolate them and send them to our program. There were 100, maybe 100 some more students from all over the district, I mean city, in and around the city. And it was such a wonderful program. We two instructors were there from the uranium side, and there were in the morning session, ended at 1 o'clock. There was then lunch. After lunch, there was another session. There was a prize giving ceremony, and we isolated. We could filter out students who interacted with us more, answered our questions, and asked also some interesting questions, thought-provoking questions that also enthused us to brand them as awardees. So it was a fun session and a learning session. So in the right portion, there are 6 groups: boron family, carbon family, nitrogen family, oxygen family. These oxygen family were called chalcogenes, nitrogen family nicogenes. It has got meaning, nicogen comes from the term nigene, a Greek word that means to choke, because nitrogen gas, if it is inhaled alone, then it will choke. Oxygen is there, that is why we are able to thrive. Only nitrogen will choke us. That is why this family was called nicogens. This is a primitive name. This chalcogens is chalkos. It has come from the Greek word chalkos, means copper. Because these elements like sulfur, selenium, they were from copper ores. They are present in copper ores. Halogens. Halos means salt. Gen means former. So salt formers, these fluorine, chlorine, bromine, iodine, these are salt formers. That is why they are called halogens. These are the noble gases. So this p block, because the last electron enters into the p orbital. This is 2p1, this is 3p1, 4p1, 5p1, 6p1, 7p1, and so on, p2, p3, p4, p5, p6. The p block. And the middle one is called the transition elements or transition metals. Why d block? This is called d block, the middle portion, because the last electron goes into a d. Why called transition? Because the last cell is not the one where electron is there. Last cell is supposing 4, but the electron will be in 3d. It's a transition from the last cell, the valence cell is the higher cell, but the electron successively goes into n-1d. If it is 4s, 3d. If it is 5s, 4d. 6s, 5d. So that is why it is transition elements. And some people say the properties are transition between S block and P block. That's okay. But the real concept has come from the electron filling from 8 to 18 or from 18 to 32. We'll not discuss more about that because our program is a balanced one. Not too heavy for class 11, 12 students, not too light for the class 11 students, not too heavy for the class 9, 10 students. So we will make a balance, more informative type rather than some deep-rooted concept. Now, this is the bottom portion, the lanthanides, the 15 elements, lanthanum and the other 14 lanthanides. And the second series is the actinide series, the bottom portion. This is also called the F block because the differentiating electron enters into the F orbital. Okay, let's sing a song. Sing the same song. I will be singing and you can have a copy with you if you want. And when we go to schools for a program, we already have printed blank formats containing 18 groups and 7 periods. There are 7 periods in the long form, 18 groups. And the fourth period, these 10 groups in the middle block, in the D block, starts from the fourth period. So we make, in the way you are watching now, we make blank formats, distribute to the participants, and then I used to sing song and they fill up, and then automatically fill the atomic numbers. Ironically, historically, atomic numbers, that was invented in 1913 by Moseley and Brooke. Then only the periodic law changed. When I will tell you the history of the periodic classification of elements, the table, at one time I was really feeling monotonous. But now when I tell about the history, but not in a very lengthy manner, very shortcut manner, you will listen to it from me. You will be feeling very, very happy how history is to be understood, to be read, and the evolution, how evolution happened, that will give you more insight, more strong, conviction to the concept of periodic classification, right? Yes, let's start. The first period, let us fill up mentally. You don't have to have any paper now because we'll have a max 2 hours program. And I'm sure if you are really a good student, you will never ever leave this program. Instead, you will love to write something in the chat box to show your enthusiasm or to ask me any question. If I know them, I will immediately answer. If I do not, then I will take time and say, yes, I'm sorry, I've forgotten. I will take time to answer your question. Right? Hydrogen, helium. Those are the two elements in the first period. First and last. Then second period. Lithium, beryllium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, number 10. 8 elements gone. Third period. Sodium, the melody is same for the S block. Melody is different but same for the P block. Melody is different but same for the D block. Melody is same but different for the A block. You will see. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, 18. Third period is over. Now, Let me share something. Now, a couple of months before, maybe in June, yeah, no, in December, this December, a couple of months, my family, I mean, staying in US, one son's family, who has a son who is my grandson of 7 years age. He somehow heard the song. It was playing here somewhere. He heard the song. Then he started, because he is an expert in mobile. He steals her mommy's mobile, sometimes my mobile. When he is with me, he has 100% access to my mobile. But he is restricted to his serial. What is that called? Mickey Mouse? No, 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 not Mickey Mouse. That 7 years old serial, and I started listening to my periodic table song again and again and again, and then found someday we are moving in some to some place in Odisha, India. He started singing in the car. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, number 10. I was really amazed. Everyone. He possibly at that time, he remembered almost all the 118 elements, being a student of class 1, standard 1 in 7 years of age. He is now in standard 2. I dared ask him, did you like grandpa's music? Yes. So that was a motivation for me. And to my utter surprise, he has a little sister, maybe 4 years old, 5 years old, maybe. No, 4 years old. He started teasing me, Grandpa, hey, hydrogen, helium, that. He has not remembered all, but she takes fun of it. That her brother is remembering all, so she should also remember something. Okay, let us not waste our time. That little girl saying, teasing me, hydrogen, helium. I laughed to my heart's content. Okay, coming to the fourth period where a transition series starts. Potassium, just like lithium, beryllium, boron, potassium, calcium, potassium, calcium. Since a transition series starts, we have a different melody. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, arsenic, selenium, bromine, krypton, 36. Now we have completed the first D series called the first transition series or the 3D series, then entered into the P block from gallium to krypton and completed fourth period. Then coming to fifth period, rubidium, strontium, rubidium, strontium. We do not have a F series to start. The same second D series comes. This is the 4D series or the second transition series from yttrium to cadmium. Let me sing in the same melody. Yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium, indium, tin, antimony, tellurium, iodine, xenon, 54. That ends the fifth period. Then coming sixth period, you have a D series and also a F series. Cesium, barium, cesium, barium. Then, earlier, this 57 lanthanum was printed here. Actinium here, 89. Now, IUPAC has said that this space and this space should remain vacant. Lanthanum to join with the other lanthanides. So there are 15 lanthanide elements and also 15 actinide elements. So I will be now singing the 15 lanthanide elements in a different melody. Cesium, barium, lanthanum, cerium, praseodymium. I'm going for a high pitch, but I have given in C, in C scale, but here maybe I'm doing in D. Yes, melodious, sweet music, integrated learning. Thank you, Principal Panda sir. Okay. Lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium. You know what is gadolinium now? I'll tell you these one. Let me finish. Lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, orbium, thulium, ytterbium, lutetium. You know, these 15 elements, along with, of course, yttrium here. These are called, oh my God, REE. Who can tell what is REE? And you know, for these 15 elements, along with yttrium, of course, here, which are called rare earth elements. REE is called rare earth elements. Lanthanides are also called rare earth elements. You know, just like, you know, Trump wanted to grab Greenland, he woke up from a deep slumber and suddenly thought of grabbing Greenland, even buying Greenland. You know what's the real reason behind it? It is REE. The whole world is now harping on having RE. These metals, the rare earth elements, they are metals, they are not abundant, but they are available. They are called rare because to extract the individual elements, the metals from the mineral is extremely tedious and difficult job. That's the reason why it is called rare. India has some resources in the earth crust, the REE minerals, but no technology to separate, to extract the individual metals. China is the hero, which supplies the REE metals to the whole world, is the hero. America wants to grab the REE because the all green energy solution is based on these elements. You know, do you know these praseodymium and neodymium earlier in the time of new lands, even to some years after Mendeleev put forth his table, for some long time, praseodymium and neodymium, they were considered as one single element, didium, Di. Maybe in the last part of 20th century, maybe in 1880 or 90, they could separate the two elements from the so-called didium, praseodymium and neodymium, and found their, you know, atomic masses. You know, not until 1913 the atomic numbers could be unequivocally determined by mass spectrometer. The advent of Aston's mass spectrometer, same year 1913, when atomic number, the proton number, the number of protons present in the nucleus, that was, you know, that was called the serial number. 1, 2, 3, 4, 5, 6 serial number. But the serial numbers up to 20, even up to 42, barring three places where Mendeleev doubted the integrity, I mean, not the integrity of scientists, the integrity of the results. He said, no, 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 iodine, tellurium, you have not correctly identified, I mean, determined atomic mass. At that time, they were calling atomic weights. Go for second determination. It's wrong. I don't believe it. Similarly, potassium, argon. Potassium was found to be 40. Potassium was found to be 39, argon 40. So how he could do? How he could place argon below sodium, below an alkali metal? How he could place argon below, potassium below neon, a noble gas? So confidently he interchanged. He said, no, you are wrong. Your atomic weight determination is wrong. Go ahead for fresh determination. So he interchanged, believing that the data were wrong. So also iodine, tellurium, so also cobalt, nickel. So then it was given the serial number 1, 2, 3, 4, 5, up to 42, all over. Even in the Mendeleev table, I will show you. I will be really excited when I will talk about history after some time. At one point of time, people think history is really boring. But I remember we used to attend our history class because our history teacher was able to emulate such passion in us. Just like he was trying to reproduce the war, Panipat war. Babur was fighting in Panipat war. Hindus are also fighting, and you will see, will be thrilled. So I may not do that kind of drama here, but I will definitely tell you something which will arouse a bit of passion in me as well as in you. Sorry. Yes, what I was saying, rare earth elements, this praseodymium, neodymium, samarium, these are the three elements mostly. They are used now to produce high power magnets, permanent magnets, and of lightweight. Small volume, lightweight, and high power magnet, those are used in electric vehicles, EVs, as their motors to run. It may be powered by lithium ion battery. That lithium ion battery also wants some critical elements. Do you know what is critical elements? Critical, these are the rare earth, REE, the critical minerals. That includes nickel, copper, manganese, and some of the rare earths, REs, and those which are of technological importance. These are called critical minerals. And even graphite, which is not a metal, which is a non-metal. Those are required in cells, not only in fuel cells, but also in lithium ion battery also you have graphite in the form of, seeds. Now these rare earth elements, they have aroused the competition throughout the world. For the green energy solution, it is the rare earth elements which have the key, the magical wand to solve the energy problem. I'm not going to go into the details how. Now let's sing. It's over. Lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium. I was talking about gadolinium. Has any one of you gone to take your MRI? MRI machine, you must have seen. You go into the machine where you stay for about half an hour. Will be taking place, and they will be taking the image of your system, whichever is you are interested in, and about cellular information can be understood. So this imaging is done by a contrast reagent, and gadolinium compounds are used as contrast reagent. You will be given an injection before entering into the MRI. What is MRI? Magnetic resonance imaging machine. So that contains gadolinium. So all these are very, very important. The coming to and then coming back again with the same melody of D block. That is lanthanum, hapnium. Now the transition from 57 to 72, because you have completed from 57 to 71. All the lanthanides are over, then 72 comes to the D block. Lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, mercury, thallium, lead, bismuth, polonium, astatine, radon, 86. Over. Then coming to the seventh and last period. Francium, radium, francium, francium, radium. Then the actinide series comes. 89 and up to 103. Actinium, thorium, protractinium, uranium, neptunium, plutonium, actinium, thorium, protractinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, formium, mendelevium, nobelium, lawrencium. Then comes to the P block. Again, the same melody, actinium to be taken again, but to have a consistent melody. Actinium, Rutherfordium, dubnium, seaborgium. This Seaborg is a scientist who was instrumental in giving this long form. The long form of periodic table, which is hanging everywhere you go, is the contribution of this scientist Seaborg. Glenn Seaborg, an American scientist. Glenn Seaborg. Over, that melody is gone. uh, Actinium, Rutherfordium, dubnium, seaborgium, borium, hassium, meitnerium, dumstatium, röntgenium, copernicium, nihonium, flerovium, muscovium, livermorium, tennessine, organation, 118. Now we know that the elements in a particular group, they behave similarly because the number of electrons in their valence shell is same. This is S1, this is S2, this is P1, NS1, NP1. Sorry, NS2, NP1, P2, NS2, NP2, NS2, NP3, NS2, NP4. All these groups will have same electronic configuration in the valence cell. Only the higher cell will increase one by one down the group. Same is the case with the D. Of course, there are anomalies, but this is D1, D2, D3, D4, there's some anomalies are there. We are not going to do that up to D10. There are 10 electrons that can be accommodated in the D subcell. 5 d orbitals. Then this is F1, F2. There are many anomalies. For example, thorium doesn't have any electron in the F. Although thorium, ironically, is in the F block. It has to be because its atomic number is 90. 89 is, has 89, you could have kept it here. Protractinium has F1. So this has to come down, be placed here, although it doesn't have a F electron. So, so what I was saying, that you see the staircase, the stair step that runs below boron. One horizontal, one vertical, horizontal, vertical, horizontal, vertical. This stair step that we have created, many tables you will also find printed one. That is a dividing line between non-metals which are to the right. These are all non-metals. These. And to the left of all these are, excepting hydrogen, of course, these are metals. Of course. And Metals have distinctly different properties than the non-metals. We are not going to discuss that. And those which are in the immediate vicinity of this stair step, like boron, silicon, germanium, arsenic, antimony, tellurium, they are called metalloids or semi-metals, having some metallic properties, some non-metallic properties. Nowadays, aluminium, carbon, selenium, polonium, astatine, they are also considered as second grade metalloids. Earlier, aluminium was called a metal. Now also it is predominantly a metal, but people have started branding them as second grade metalloid. Aluminium, carbon, selenium here, polonium, astatine, although they are adjacent to the stair step. Now, comes the controversial discussion. How many natural elements? How many synthetic elements? Different books will have different number. Some will say 92 up to uranium here. Some will say up to plutonium, 94. Some will say 90. I'll say why they say 90. Some will say 88, some will say 87, some will say 86. So there will be varying number. To me and to the IUPAC, it is 94. Because in 1940 and 41, just before the World War II, the neptunium and plutonium were discovered in nature. And it was synthesized in large scale. Of course, it is synthesized because to get a large quantity of plutonium, to have a plutonium bomb and drop it in Nagasaki and completely wipe out the contours of that city, Nagasaki, was the plutonium bomb. And Hiroshima was struck with uranium bomb. They were experimenting in 1940-41. This plutonium was discovered. And they, of course, it was discovered not in large quantities. It is there, but they had to prepare synthetically to prepare a large quantity of plutonium 241 and made it a fissile material for the plutonium bomb dropped in Nagasaki during World War II. So before that, these two elements were discovered in nature. So 94. But, their natural abundance is almost negligible. So we can delete them. But for practical purposes, we call elements above plutonium are transuranic elements. Transuranic. Literary meaning is that after uranium, but practically after plutonium. Of course, you can take after uranium because neptunium, plutonium are now synthesized synthetically by some other technique, not extracted from nature much. And interestingly, let me tell you, before we settle down how many number is the natural elements, how many synthetic, before we settle down once for all, let me tell you that up to bismuth 83, all the elements are stable. They are not radioactive. Let me tell you, radioactive elements or isotopes are those which are unstable. They continuously emit some particles from their atomies. Nucleus, alpha, beta, or positron. They are particles coming with high speed. They are called rays, but actually they are not electromagnetic radiations. They are simply particles with high speed, looking like rays. But in fact, as the slogan now, everywhere in the world you go, even in the US market is popular, buy two, get three, get one free. Buy one, get two free. Buy one, get one free. So alpha, beta, when they come out, the free is the gamma photon, which is not a particle, which is an electromagnetic radiation, high energy radiation, that is a consequence of alpha decay, beta decay, positron decay. So alpha, beta, gamma we usually say, but alpha, beta, positron, they are particles, while gamma is a massless particle. We call it photon. Okay, let's not go to that area. So up to bismuth, all are stable. They are stable means they are not radioactive. But before that, there are two exceptions. Technetium, which was discovered very late as 1939, before the discovery of plutonium and neptunium. Technetium, a place that was left by Mendeleev. Hats off to Mendeleev. I salute Mendeleev because his creation of table is based on properties. He made 62 cards at that time, 62 elements, writing the formula of their oxides, hydrides, chlorides. And then while we was traveling, maybe in train, everywhere he was sitting, he was taking all the 62 cards with all their properties written, formula written, as playing card game, which are matching, whose formula are watching. They were keeping the same column. Of course, with increasing atomic mass, he was not interested in arranging in horizontal manner. He was interested, just like Newland, a musical genius. He was influenced by Pythagoras' musical analogy. But Mendeleev was the true scientist in the sense that he was grouping them in a column and finding a lot of empty space, and he said there will be new elements coming up. During his lifetime, this element below boron, I will show you there, scandium was discovered during his lifetime. Mendeleev gave periodic table 5 times, out of which 3 times are very important. The last before his death in 1907. At that time, my grandfather was born. Yeah, he was born before my grandfather was born. My grandfather was born in 1885. He was born much before that, but he died in 1907, while my grandfather died in 1969. Maybe 50 years senior to my grandfather. So when he died in 1907, before that in 1905, he gave his final table. Because it's not like long form. Everyone clubbed together in a sort with 9 groups, not 18, 9 groups last. I'm talking of after noble gases were discovered. Not in 1869, his first periodic table. Not in 1871, his second periodic table. At that time, noble gases were not discovered. They were discovered suddenly from 1990 to 2000. Only in 2000, I mean, 1890 to 1900. I'm so sorry. 1890 to 1900. During these 5 years, a fellow called Ramsay was so intelligent. He traveled from place to place and collaborated with different scientists of Europe to quickly discover all the noble gases. Helium, argon was first, then others. Helium, krypton, xenon. Radon was also a place was left vacant below xenon, and maybe, yes, before 1907, radon was discovered, which was radioactive. So before bismuth, all are stable excepting technetium 43. A place was kept vacant. Mendeleev could not see the discovery of technetium, which is radioactive, but is almost extinct. Some people, they do not consider technetium as natural, but it is there. However insignificant amount it may be, it is there. Hello, Mr. Plixer official. Plixer. Who can you just tell your name? Plixer is very yeah. I see your message. Hello, sir. Hello, Plixer. But who are you? Please write your name. Uh, yeah. What I was saying. What I was saying. What I was saying. What I was saying. Yeah, about Mendeleev. So these are the two elements which are now almost extinct. They are synthetically prepared, but they are naturally present. They were discovered in nature, and the other one is promethium. This space was lying vacant for a long time. Promethium 61 is a rare earth, RE, but it is. I will be putting a star over the radioactive element. These are the only two which were unstable, radioactive. Others are stable up to bismuth. Then from polonium, astatine, radon, francium, radium, actinium, and all the actinides up to lawrencium, and then the heavy, super heavy elements from rutherfordium up to organation, these are all synthetic. So to me, 94. To some, 92 up to uranium. And some, because polonium and astatine, they are present in almost insignificant quantity. So they delete. Also francium, which came very late after the death of Mendeleev. Francium also is present in a very, very insignificant quantity. And technetium and promethium. So some take out technetium, promethium, neptunium, plutonium. So 90. They say 90. Some remove polonium, astatine. They say 88. Some remove also francium, 87. So there are different numbers floating. But to me and to IUPAC, naturally occurring elements is 94. And there are two liquids. One is bromine as a non-metal, Vr2. It remains as a diatomic molecule, as a red liquid at ordinary conditions of temperature and pressure. The other one is mercury, which is a metal, is a liquid at room temperature. But for Indian point of view, in hot climate near the equator, some more elements have been considered as liquid, like gallium. In Indian point of view, you'll say gallium is a liquid because its melting temperature is near 30 degree. So if you hold it in your hand, it will melt. It will look like mercury because our hand's temperature is about 37 degrees Celsius. The gallium's melting point is 30, so it will immediately melt. Same is the case with cesium, same nearing 30, but don't do it in your naked palm. That will pierce through your palm and come out. You'll go to the hospital because cesium is an alkali metal stored. All these are stored inside kerosene. So don't do that. You wear a glove and then hold some cesium. You will find it will be after some time feeling like mercury. But mercury is heavy, cesium is not that heavy. So it will be liquid. And francium also is radioactive, is very scantily available, but it also has a boiling melting point about 20 something. So it will also melt. And some people take rubidium. Rubidium melting point is about 37, same as our body temperature. And in hot condition in summer, when our weather conditions, the temperature goes above 40. Now in India and some other countries, you will find in April, slowly the temperature will shoot up more than 40. So in that condition, inside kerosene, you will mark, rubidium is a liquid doing some disco dance. Rubidium. So we can say rubidium, cesium, francium, and gallium as liquids, but you could ask an American guy or a Canadian guy, he or she will say only two: mercury as a solid, bromine as a liquid. That's it. And interestingly, up to californium, americium, curium, berkelium, californium, you know, these elements can be synthesized, has been synthesized in some large quantity, and they are being used for several practical field. But beyond californium, einsteinium, fermium, they are so short-lived. They're all not only synthetic but also radioactive. Their half-life periods are extremely small, maybe some few minutes, few days, few hours, few milliseconds. So their practical application is not now considered. Maybe some more time will be required till we can accumulate immediately some more quantity of Einsteinium, fermium, mendelevium, nobelium, lawrencium, rutherfordium, dubnium, seaborgium, and harness them in some field. But up to californium, yes. Because up to californium, the half-life period, because I tell you, every radioactive element has a half-life period. For example, uranium is about 10 to the power 9 years. A billion year for every gram of uranium to reduce to half of its amount, you have to wait 10 to the power 9 years. 1 billion years will be needed for any amount of uranium to be reduced to half, and then that half to reduce to one fourth. I mean, half of half, that is one fourth of the original value, will take another billion years. So they are long lived. They remain. Jab tak rahega, in I'm talking in Hindi. If you are an English guy, don't worry, I will explain to you. Jab tak rahega chand aur suraj, tab tak uranium rahega. क्योंकि क्यों? Why? Because uranium has a half-life of 10 to the power 9, around 10 to the power 9, more than that, 1 billion years. So it is believed when Earth, the entire universe was created by Big Bang. So from those time, after some time, of course, when fusion happened and many new elements are formed, during those time, uranium is there and it will remain for ever. So every radioactive element has a half-life period. Those which have got a small half-life period, they will die soon, because when it will decay, it will have another daughter. Another daughter, we call funnily daughter. It's different from mother will be there because its half-life period is high. Mother will be there and daughter will be there. Daughter will also sometimes be radioactive. It will produce another daughter. So main mother, daughter, granddaughter, everyone will continue to remain as per their respective half-life periods. If it is small, they will perish. They will go to almost extinction, just like the plutonium and neptunium have become extinct. So also technetium and promethium, that will happen for those having a very small half-life period. Anil sir, namaskar. Now, before we talk about, I think we are inching close to our final time to say goodbye for the periodic table day. I told you why we are observing today. And in fact, we are observing throughout the year. Whenever any school or any district education officer they're inviting us, our group is going to their school with our resources, prizes, We used to provide a in very, very good looking printed cup, a mug rather, containing the latest modern periodic table. And we ask the student who receives this prize to keep it before him or her in the study table and always converse with the table so that he will remember everything. I will give you these files which I'll be using now in the description box. Those who will be interested can download. I have already told this. The configuration, the entire group of elements have same identical valence cell configuration, except their n value, the principal quantum number of the last cell will go on increasing one by one down the group. The boron family, the carbon family, the nitrogen family, the oxygen family, halogens, group 0, the noble gases. Then the D block, group 3 or 3b, it was earlier called 3b, 4b, the titanium group, the scandium group, the vanadium group, the chromium group, the manganese group, the iron group, the cobalt group, the nickel group, the copper group, zinc group. And I urge upon you, those who are in class 9 or 10, or you have your own blank periodic table format and start singing the song. Put the elements as you continue to sing, pause, you start the music. You can also watch the ASAP American music also and see, compare. Theirs must be much better than us, because those accents are American accents. And the pictures they have given, might be some similarity will be there, because we have selected only one typical application picture. Just to remember, fluorine, we have given a dental, a toothpaste. This fluorine is present as fluoride is present in toothpaste. So every element has a catchy application picture that will be instrumental for the memory, storing in the memory cells. And this is the zinc group, then the F block, the lanthanides and actinides. Stair-step, I have already discussed. The second grade metalloids. Yeah. If you want to find the atomic numbers, you can use this periodic, which we call the magic numbers. It's not really magic, but earlier, in the time of Newlands, the periodicity was 7, 7, only 7, 7. After 7 elements, the 8th element is a recurrence, a repetition. Even during the maybe 30 years, 40 years of Mendeleev's era, it was 7, 7, 17, 17. In Newland, I will show you, he failed miserably because he could not grade them according to their properties. He placed them in a horizontal manner, in a manner of increasing atomic mass without knowing how many gaps will be there between one to the other. Will there be any other to be discovered? He has no foresight. He only said, yes, there will be a fixed pattern after every 7 elements. The 8th element is repetition. So during Mendeleev, it was 7, 7, 18, 18. 32, those lanthanides were not all discovered. At the all were not known. Many DDM was there for a long time, neodymium, praseodymium, as only one metal, as one element, DDM, which was deleted. And promethium was not discovered, many other, cerium was known. Cerium was long since known, erbium was known, all since. But many were not known. So, but 1905, when noble gas were introduced as a ninth group, then the magic numbers of periodicity changed from 7 7 18 18 to 8 8 18 18. For example, lithium is 3, add 8, you will get 11 sodium. I'm talking of atomic number, not atomic mass. 11, you add again 8, 19. Then 18, because D series has already gone. 10 electrons have already been, 10 elements have been already added. So this is 37 rubidium. Then another 18, 55 cesium. And finally 32, because F series has already gone. 87 is francium. So for S block, the magic numbers or the periodic numbers are 8, 8, 18, 18, 32. You don't forget about the first period. Start from lithium. So also from beryllium. For the P block, you have different number. 8, once 8, then 18, 18 two times, 32, 32 two times. Because it is coming, this nihonium, plerobium is coming after the D series. That is why it is 14 plus 10 and 2, so 32. 32 two times, 18 two times, 8 one times. For example, boron is 5, add 8, 13 is aluminium. Add then 18, not 8. Just like you have done 2 times 8, here you have to do only 1 time 8. Then 13, then 31 is gallium. Again 18, 49 is indium. Then 32, 81 is thallium. And then nihonium is again 32, nihonium 113. Same numbers will be applicable for all the groups. And once you know it is calcium is 20 and gallium is 31, you just write down. There is no need to go down the group. Rather, you connect serially from 21 to 30, completing the first transition series, similarly from 39 to 48, the second transition series. Then since the third transition series is preceded by the lanthanides, so 57 to 71. Then after that, 72 to 80, the third transition series. Same thing happens in the fourth transition series. Since 89 to 103 is actinides, then we come 104 to 112, the fourth transition series, and then onwards the P block, 113 to 118. You know why it is written UUE? Before, when I was teaching, 10 years before, maybe 15 years before, these elements were not given the name like dubnium, seaborgium, borium, hassium, meitnerium. It's not there. Because, just like we fight with each other, you friends fight with each other, scientists also fight for each other. Now, there are 3 groups. Mainly 3 groups at that time. Japan has just now joined. One is Russian group, the other one is Russian group in Dubna, and Germany, Darmstadt, Germany, and US in California. So these 3 groups, they do this new synthesis of new elements. They have no work. Their sole work is to find new elements. How they do? I used to funnily say, they go for, bombarding. Supposing, you, Mr. Say, Plixer is standing here. He's a target. Take any metal as target, say palladium or silver or samarium, any as target. And take a particle, maybe alpha particle, maybe proton, maybe neutron, maybe a heavy particle like beryllium, like sodium. So put it under a cyclotron device, now called synchrotron, which will, in the presence of magnetic and electric field, will give a high speed. So it will be gaining higher and higher acceleration, and when it will acquire high speed, very comparable with the speed of light, not exactly equal to, maybe 1/3 or nearer to the speed of light, then that particle, that projectile will be hit on plexer, I mean the target. Target will be, supposing I am the target, I am sitting, I am standing, and a high speed particle now will hit me, will penetrate into my tummy. So that particle, say alpha or copper or any particle which is in a high speed projectile coming from a synchrotron or a cyclotron, will enter into the nucleus of me, means is standing, is target, and then my tummy will hurt, it will be unstable, and after some time I will be transformed magically to another element. My entire contour, my nose, my eye lines, my eyebrows, all will change. I will be a different person, and from the backside another small particle will go out, will be ejected out. So this business they do, they take a trial and error, some target, the heavier element is taken as target, isotope is taken as, and a lighter isotope, may it be copper, may it be zinc, is used as a projectile and hit it, and they get new elements. That is their, work throughout the session. They quarrel. All these elements, when they were discovered, every group wanted his name or the country's name or city's name to be the name of the new element. When they quarreled, then IUPAC said, no, nothing doing. Keep it the Latin name. Supposing this is 105. So when before 20 years, it was discovered, but it was called un. Un is for 1, nil is for 0, and 4 is quad. And one ium is to be suffixed, ium. Un nil quaddium. And this is un nil pentium, W. Un nil hexium, un nil heptium, un nil octium, nonium, ennium. 109 was called un nil n, enn, eum. Un nil ennium. 110 is un nilium, un ium, ununium, rondgenium, un bium, bi, or un bium, or bium, copernicium, un trium. So in this way, this one is will be discovered very soon. When you guys will be in your in college, maybe you'll be hearing this un ennium. They had tried. Those mad guys, they have tried already but failed. They could not get a single atom. I'll tell you how. See, they have tried. They are doing their business. Otherwise, they can't get a good sleep. They have to keep one as a target and the other one, put it in the synchrotron and put it, give a high speed and then hit. Then see what happens. They are in such, they will succeed, no doubt about it. Now, these radioactive elements we have done. And let me tell you, which I had not told yesterday, yes, I can tell you here, there are some lighter elements like potassium, like carbon, like hydrogen. They have some less abundant radioactive isotope. For example, potassium. Potassium 39 is the most abundant isotope, 99.9%. But 0.012% is potassium 40 isotope, is there naturally. 0.012%, that is radioactive and is a beta emitter. Potassium 41 is also there, little more percentage, but it is not, it is stable. Ironically, we teach to higher level students why potassium 39 is stable, potassium 41 is stable, and potassium 40 is unstable, is a beta emitter. Same, carbon, natural carbon, coal everywhere, human being, trees, everywhere where carbon is there, you find carbon 12, 9, 99, 98%, 98 point about 8, 9, 98.9, and carbon 13, 1.1, nearly 1.1%, and carbon 14 is very, very negligible. It's not counted. 10 to the power minus 5%. So it's not counted, but it is there. So that carbon 14, not carbon 13, is not radioactive. Carbon 14 is radioactive, is a beta emitter, and that is present everywhere in our body also. Now, I used to say funnily that a human being like you or me is radioactive because we carry potassium 40. Because we take a lot of fruits, particularly banana and other fruits, they have potassium. Potassium means potassium 40, 0.012%. They are emitting beta particles. Carbon 14 is there, that is emitting beta particles. So per minute, our body is emitting about 7,000 beta particles per minute. So we are radioactive, but nothing is happening to us because there is every thing, for any bad thing, there is a limit. So the alpha, beta, gamma rays, they are harmful to human beings. But up to certain limit, it will not cause any harm. But beyond that, it will cause serious health hazards. So that's what I was saying. Now, yes, I've given the names. These I have already discussed. And modern periodic table, modern periodic law, during the time of Mendeleev, atomic mass was the basis. Whichever switch he made, he did it by confidently telling you guys have not experimentally determined correctly. The atomic masses are wrong. Do it, go and do it again. But they were correct. Mendeleev was wrong, but he nicely arranged them according to their properties, leaving a lot of empty space. And then when Moseley invented atomic number, then the periodic law changed. The physical and chemical properties of elements are periodic functions of their atomic numbers. All they were conforming, agreeing to their increasing atomic numbers, not though in some cases increasing atomic weights. This you already know. Bridge elements are the second period elements. They are called bridge elements. And third period elements are called typical elements. And there is a diagonal relationship between second bridge elements and typical elements. Lithium and its diagonal element magnesium. Beryllium, its diagonal element aluminum. Boron, silicon, they have some similarities, and this similarity is called diagonal relationship. Noble metals, have you heard? You have heard noble gases, but noble metals are 8. Rhodium, ruthenium, rhodium, palladium. This is the second triad. 8, 9, 10, group 9, 8, 9, 10 in the D block. And this is the third transition series, same 8, 9, 10. Osmium, iridium, platinum. This triad and this triad 6. And in group 11 or 1B, silver, gold. These 8 are called noble metals because they not easily corrode. They do not rust. I mean, I'm telling rusting word is meant for iron. So the common word is corrosion. They do not corrode or they break down. So they are resistant to atmospheric ingredients. They're resistant to corrosion. And they do not also react with dilute acids. That is why they are called noble metals. And what is PMG? PGM, platinum group of metals, is same the two triads, rhodium, ruthenium, rhodium, palladium, osmium, iridium, platinum. These 6, they are called platinum group of metals because they occur together in the same minerals. They are also noble, but they are silver, gold, they are, though noble, they are not platinum group of metals. Super heavy metals is beyond the end of actinide series, beyond lawrencium. That is from rutherfordium to organesium, they are called super heavy metals. Same as trans-actinide elements, same as super heavy metals. Ferromagnetic metals, iron, cobalt, nickel, gadolinium. The gadolinium is my favorite rare earth because I have consumed, because I had once my MRI. I have taken gadolinium injection gadolinium. So these are ferromagnetic. They can be converted into permanent magnet. But for making permanent magnet, nobody is now caring these. Rare earth. Of course, gadolinium is rare earth, but praseodymium, neodymium, samarium, they are the heroes. So they are not only are attracted by magnets, but they can be converted to permanent magnet. Transformium elements above fermium, above 100. I have told you up to californium, synthetic elements have been synthesized to some extent in bulk quantities so that you can do something with it, because their half-life periods, americium is for 458 years, berkelium is 1380 years, californium 351 years. But you see others, the last one, organeston, is 0.9 millisecond. The moment it will be burned, it will die. Tennessine 112 millisecond. I'm going backwards. And see, Einsteinium is 39.8 days. So we have to have a lot of Einsteinium to harness it. Temporary name I have already told you. Isotopes, this is this file will help you a lot to your teachers. I've listed all the 118 elements, how many stable isotopes are there, how many monoisotopic, the 19 monoisotopic elements, how many radioactive natural isotopes are there, and what is their average atomic mass. All these I've given for all elements in the file. Okay. Now within a small little time, I will talk about the history and finish. Unless we, do some historical discussion on history, not historical, discussion on history of periodic classification, our program is incomplete. Celebration is incomplete. Why? 7th February, I have already told you. And one teacher, Staneker of Kentucky, US, he initiated it maybe 15 years ago. Now, whole US is celebrating on this day. Newlands put forth his initial periodic table, law of octaves. I'm not going to elaborate things. Dobrynin's tried, in 1789. Lavoisier was the first to put forth a list of elements, not in any systematic manner. In an erratic manner, he took light and heat. He was calling caloric as elements. How surprising. 33 elements included light and caloric. And chlorine was called muriatic radical, fluorine, fluoric radical, boron, boracic radical. So this was then 1789, this is 1817, came Dobriner. For the first time, he indicated that there must be some mathematical relationship or reasoning for the recurrence of similar elements. He found 3 triads. Later, during the last part, he added another triad. Lithium, sodium, potassium, they are chemically similar. Why? Because he said the average atomic mass of the first and third is nearly equal to the atomic mass of the middle. Same is case for calcium, barium. Its average is same as strontium. Chlorine, iodine, its average is same as bromine. And finally, sulfur, tellurium, same as that of selenium. The first hand information about a mathematical relationship between the similar elements that came to the mind of Dobriner, but it could not work. It was rejected. Then came Sa re ga ma pa dha ni sa do re mi fa sol la ti do C D E F G A B C. So that law of octaves, see how interesting. For few elements, it is okay. Start from sodium or say fluorine. Take fluorine as 1, 2, 3, 4, 5, 6, 7. After 7 elements, the 8th element is chlorine, which is also a halogen. Say sodium. After 7 elements, the 8th element is potassium. Okay. But what about copper? Coming to rubidium, it will come after 14 elements, not 17. Because, many were not, scandium was not discovered. He did not arrange them according to their properties or formula of oxides, hydrides. And so he just took the atomic mass and graded them without knowing if there will be any more element to come or not, nothing. So from potassium to rubidium, 14 elements. 1, 2, 3, 4, 5, 6, 7, one place. 8, 9, 10, 11, 12, 13, 14 के बाद आता है is coming rubidium. 14, then 14. Then this 14 became 17 as other elements were discovered in between them. Vanadium. Vanadium was there. Vanadium. No, vanadium was not there. Scandium and vanadium joined. And Didium at that time, didium is here. It was later known as a mixture of two rare earths, praseodymium and neodymium. Rhodium was called Ro. Actually, it was given the symbol RH. RH. Rhodium, not Ro. And beryllium was called at that time glucinium, Z. Boron, the symbol was Bo, not B. So this was rejected because it failed after calcium. Only for few elements it's okay. But yes, the central idea after 7 was there for a long time till 1905. It became 8. But that concept, musical concept, is really, hats off to Newlands. So American guys, I fully endorse. They did not take 8th February, they took 7th February. You Google search now today. National Periodic Table Day. You will find 7th February and you will find when. Maybe 10-15 years before they started. Just like they were doing Mole Day every year on October 23rd from 6 a.m. to 6 p.m. We are also doing here. They have, for the last few years, they have started observing Periodic Table Day. A lot of things, time will end, but discussion on periodic classification will never ever end. So here, that was the table. I have recreated the table here. Now see, 1, 2, 3, 4, 5, 6. The similar elements are now in his table were found in a row, not like Mendeleev in a table, in a row. Copper, nickel is coming along with fluorine, bromine, iodine, platinum, iridium also. Sodium, potassium is also occurring, copper, silver, and thallium. Okay, cesium, rubidium is okay. Magnesium, calcium is along with zinc. Strontium is okay. And this is cadmium is called Bd. And barium, vanadium is also coming here. It's very funny. Many were missing. So it was rejected, in fact. Law of octaves was rejected. Then came this fellow, Newlands. He died during a surgery when he was 61. He had some problem for which, because he was a London guy, he had a lot of surgeon friends. He said, you come and do the surgery at home. Maybe some small little hernia or something operation. He did it at home. But it became complicated. He died because of the post complications, surgery complications. He died at the age of 61. Mendeleev gave the first table. You see the first table. This was the first table where, like Newlands, the similar elements are found in a row, what we call period. Titanium, zirconium, there was no hafnium at that time. But he predicted hafnium will come. Vanadium, niobium, tantalum, okay. Chromium, molybdenum, tungsten, okay. Manganese. This was wrong. Manganese is below a technetium, 43. I mean, I'm talking of atomic number. These are all atomic masses, rounded up to the nearest 0.5 or nearest number. So below manganese, rhodium, Platinum, there are all places were wrong. Iron, ruthenium is okay. Osmium is not there. Osmium is here. Iridium should be in cobalt. Nickel, cobalt was together. And you say, this is, what is this? PL. What is PL? Palladium or something like that. Osmium. So the positions are all wrong because of their wrong atomic masses. Uranium was called UR, whose atomic mass they got 116. Can you believe? It was really 238. At that time, the equivalent mass was the basis. Atomic mass is equal to equivalent mass into valency. Equivalent mass was determined experimentally. How many grams of that element combines with 1 gram of hydrogen or 8 grams of oxygen? That we got equivalent mass. Then into valency is atomic mass. So since these they exhibited variable valency. So if you multiply by 2, you get 2 times less. You multiply by 4, you get 2 times more. So actually valency 4 was needed. So many, this orbium is 56 while it is really 1678. Yttrium, it was not YT. Really 88 is 60 at that time. Indium is 75.6, is really 113. Cerium 138, but at that time 92. Lanthanum wrong. 180 is also wrong. Later it was found 180, but that was also wrong. Didium, which was not really a one element, is two elements, 95. But it must be average. Thorium is really 232, it is coming 118. So because 17 elements have absolutely wrong atomic mass, their positions could not be proper. And then in 1871, he gave the second table where the gaps are well marked. Below boron, there was one gap, which is called Echo boron or Eka boron, just one place below boron, that was filled up during his lifetime. I'll show you in the third by scandium. Eka aluminium, although boron, aluminium, they belong to one family. So also indium. So also below aluminium, that element was discovered gallium. Scandium belongs to a different family, but at that time there was only one group 3. Later they divided into group 3A, 3B, 1A, 1B, 2A, 2B, and so on. Now he also predicted an element below silicon, Eka silicon, which was germanium in his lifetime. Also below tellurium, Eka tellurium, which was polonium in his lifetime. But there were many. Ninth period was entirely free because there was a drastic jump from 138 to 178. He thought there could be many more elements. Let me leave a complete period. There were 12 periods in his table and 8 groups. The 8th group was erratic. They did not have, they said iron, cobalt, nickel, ruthenium, rhodium, palladium, osmium, iridium, platinum. They were transitional elements. They are anomalous. So they could not fix any subgroup. But he interchanged between cobalt and nickel because nickel, palladium, platinum, they were behaving similarly. Therefore, despite the fact that the actual atomic mass of cobalt was found to be higher than nickel, but still cobalt was kept with rhodium and iridium. So that he made. He said your calculation is wrong. Although it was not wrong, cobalt has a higher atomic mass, but atomic number wise it is 27 and 28. And in his table, I have deliberately avoided, there was copper, silver, zinc was also here as well as repetition here. So to avoid repetition, I have deleted copper, silver, gold in group 8. And didium, cerium, erbium, lanthanum, their positions were wrong because I told you their atomic masses were wrongly determined. Lanthanum should come after barium. It is here. 180 is not 180, it is something else. Cerium, it should be along with lanthanum, lanthanide series. Didium also in the same lanthanide. Erbium, all these 4 belong to the same lanthanide series. You will see. And that Eka boron, Eka aluminum, Eka silicon, Eka tellurium, Eka xenon was also, Eka xenon, I will tell you that during 1884 and 1900, all the noble gases were discovered by a famous scientist who was main instrumental, is called Ramsay. So all the noble gases were discovered. A new group was appended. During that time also, another noble gas, radioactive noble gas, radon, was discovered. Finally, he gave, before his death, 85 elements with a new periodic table. Scandium has come up. Scandium has gone to a different subgroup. A, B subgroups were done. Boron, aluminium, they belong to a same group. So also gallium, indium, thallium. And this is B group, scandium, yttrium. Lanthanum was kept proper in the proper place. Actinium also kept in the proper place. That cerium has a wrong position because at that time they could not, put it here. It should have been starting from here. But it is still there. And there was no actinides. All the four actinide elements which were discovered by that time, thorium, protactinium, uranium, they were there in the main table. And some gaps were there. Ecum, manganese, which will be taken by technetium. I told you the radioactive element. Then Dewey manganese is rhenium, which will be discovered later. Then, iodine was given the symbol J. You don't think that J by is a printing mistake. No. They were saying I, small I, capital I, they will be confusing. So iodine was the name, but they were giving symbol J, which finally was deleted, was replaced by I later. It was J. Radon was discovered, so radon was put. Then finally, and after the inclusion of, see, group 0 is in the extreme left in the last table. So there were now 9 groups. The ninth period, which was vacant, is no more there because the other lanthanide elements which were discovered by that time, he kept it separately. This 61, of course, I am saying 61 now because I know the atomic number. At that time, atomic number was not known, but a gap was there at that time. Now I will tell you the main story. This, during that time, Lothar Mayer, he made similar contribution, not different from, he was a friend to Mendeleev, but he made some contribution very similar to Mendeleev. We will not discuss about Lothar Mayer's contribution. Now, I will be talking about this Moseley. This is a great person who, with the help of this van der Broek, invented with the X-ray spectra, famous X-ray spectra, the number of protons present in the atomic, the atomic number. He found that up to atomic number 42, I mean up to serial number 42, all the elements were by that time discovered. The serial numbers became atomic number. Very interestingly, 1, 2, 3, 4 up to 42, molybdenum. Every element was discovered and that serial number became the atomic number. But there was then a gap, 43 is missing. 43 he left. So he was instrumental in creating more spaces which could not be possible by Mendeleev. 43, it was taken up by technetium, 1929. Then 61, promethium, rare earth. Then 72, that is below hafnium, below zirconium is hafnium. In the place of hafnium, they have written, this guy, Mendeleev guy, he kept below hafnium, zirconium, sorry, he kept cerium. So cerium was sorted to this place, and the actual position of, the place below zirconium was hafnium, which was solidly predicted by whom? By Moseley. Moseley. This is hafnium. And finally, at that time, below manganese, one place below manganese was invented much later. But 2 places below manganese was invented earlier, 75. This is rhenium. 2 places below. I have given the dates. Rhenium, 1925. By that time, Mendeleev was gone. Dewey manganese. But echo manganese was 1937, much later echo manganese. But Dewey manganese was invented or discovered earlier. Then below cesium, francium was discovered. Below below iodine, another radioactive element was discovered 1940, before the World War II, is astatine. So, and it was the long form that you see. What first? Deming was the USA scientist who first time split out into a long form, separated A and B group and put the B group in the middle portion, but still there were a lot of problems. And finally that was sorted out. And when mass spectrometer was invented, I should say invented by Austin, that could give the exact isotopic mass. If you consider tin vapor, there are 10 isotopes and 10, all the 10 were giving different isotopic masses. 112, 113, 114, 115, up to 121. The average is 119. That was given by chemical method. But in spectrometer, mass spectrometer, all the isotopes were giving the exact isotopic mass. Even many places after decimal, when the technology was improved, high power magnet was created, the resolving power of the spectrometer was increased at that time, and then everything was sorted out. When atomic mass was 100% correct, then everything was sorted out. Atomic number was already determined by Moseley and his workers. Seaborg is the scientist who has been named, one of the elements has been named after him, seaborgium. He actually gave the long form that you are looking is the real creation or proposal of Seaborg. He gave, at this time there were many elements were not known. Uranium, neptunium, plutonium were taken in both. It was taken, but still it was finding place in the main periodic table. They were taken. The actinide series have started. 61 was still vacant at a time when he proposed in 1945. You see, then now what you are saying is complete in all respects. And the father of periodic table, today we salute you, Mendeleev, but he was a little controversial and he was socially little unpopular in Russia. So he was not given the Nobel Prize. People believe that he is a Nobel laureate, but he is not. He is to be given Nobel Prize, but he was not given. In his place, some other person was given. When he died at the age of 72, he said, being a scientist, he said, "Doctor, you have science." See the irony. He was a scientist, but now he turned into a believer. "Doctor, you have science. I have faith. You cure me." He died of influenza only. Heavy, high fever didn't go. And Mosley, before I close, I'll tell you how Mosley is great. In fact, on this day, August 10, I will make another periodic table day. I will consider him as a hero. He died at the age of 27, young man. Before 27, he invented atomic number. Can you believe it? And not here in India is popular. In Western countries, every degree, if you will get a bachelor's degree or MS degree, you have to go to serve the army for 1 year. If there is war, you have to go to the war front. And he had to go. 1915 was the First World War. So he had to go. He had to be deputed to Turkey. Gallipoli, he was at war. I mean, he was in the war front. He died. He died while fighting in the war front in World War I at the age of 27. So age is not important. What we contribute during a small time that we are living here, that is important. Guys, we close this session. If you have liked the 2 hours, little more than 2 hours of deliberation, you hit the like button. As it is customary for any YouTuber to tell, Otherwise, people will think bad. Hey, you are not asking for vote. I'm sorry. It's not a political, contest. So if you like, hit the like button. And if you also benefit, you can subscribe to my channel. We are having programs, study programs in chemistry mostly, and physics also, for school level, and 9, 10, 11, 12, both in Odia. In my mother tongue is Odia, and an Indian language, and in English. So if you want in English some topic of chemistry, you can ask me. I'm just writing down my WhatsApp. Today is WhatsApp, globally connected. 09437094370 64155 is I have given the chat box 94370 64155. Bye-bye. Thank you so much. And within 2 minutes, I'll be putting these files in the description box. You can have it. Bye. Have a great day. Happy Periodic Table Day.